Okay, so let us start the video by recalling theorem 2.9. which is about this Diophantine equation. We already know what a Diophantine equation is, at least in two variables, and which is linear, which looks like this, where a, b and c are integers, x and y are variables, and such that a and b are not simultaneously 0. Also, a solution to this equation is a pair of integers. Now, this theorem tells us that such an equation has a solution if and only if d divides the right hand side integer c, where d is the greatest common divisor of a and b. And when this condition is met, and hence when there is a solution, say these integers constitute any particular solution, then all the solutions to the equation are given by these expressions: plus b divided by d times t, and y equal to y naught minus a divided by d times t, where t is an integer. In fact, t is any integer. From these expressions, we have already discussed these things, but let me just say it once more. We can see that since d is the GCD of a and b, these quotients b by d and a divided by d, these are actually integers. Now, naturally, there is a corollary to this. Which considers a special case, namely that case where d is 1. So if it goes like this, if the GCD of a and b is 1, that means if a and b are relatively prime or co-prime, and if x naught and y naught, this pair, is any particular solution of the linear Diophantine equation ax plus by equal to c, then all the solutions to this equation are, so we just have to put d equal to 1. That means x equal to x naught plus bt and y equal to y naught minus at, where t is an arbitrary integer. That way also you can write, or you can just simply write it like this. So this is a special case. Okay, and you notice one more thing. Why are we not saying anything about whether the equation is solvable or not? Because only after it becomes solvable, the question of writing down all the solutions comes. But in this case, it is yes, it is solvable. Why? Because here the d value is 1, and 1 divides c no matter what the integer c is. So now to illustrate this special case, the author has given one example. And that example is this. Consider the Diophantine equation (5x plus 22y equal to 18). Linear I should have written, but because one can see that it's linear, so there is no need to write it explicitly. However, if you do not write Diophantine equation, although you may be in a discussion about Diophantine equations, but if you do not write Diophantine equations, then it may mean that this is just a simply linear equation. When we write Diophantine, we mean by that that we seek integer solutions. That's why we use this Diophantine adjective. Now, okay, so now what is the GCD of 5 and 22? That is 1, because 5 and 22 are relatively prime. 5 is a prime which does not divide 22, that's why. So that means we can apply this corollary. But for that, we first of all need a particular solution, and one such solution is this. The integers x not equal to 8 and y not equal to -1. Am I writing these correct values, or am I just simply going on writing whatever I like? No, it's correct. Integers form a solution to the above equation. So all the solutions are, we just use these expressions, x equals x naught plus bt. That means 8 plus bt. Here b is 22, so 8 plus 22 t. And y equals y naught, which is -1 minus 80. Here a is 5, so minus 5t, where t belongs to z. The fact that all the solutions are in fact this, it means two things. One of them is that for any integer t, these two will constitute a solution, and the second thing is that any solution actually has already been accounted for in this list of solutions. So that's why they are the only solutions. Okay, now Diophantine equations, now then the author writes, Diophantine equations frequently arise in solving certain types of traditional word problems. It is in fact through some types of word problems they were popularized. And to see how, one example is there. In this type of problems, Diophantine equations arise naturally when you try to model these problems mathematically. A customer bought a dozen pieces of fruit which are apples and oranges. For $1.32, that means $1.32. If an apple costs 3 cents more than an orange. And more apples were bought. More apples than oranges were bought. Oranges were purchased. How many pieces of each kind were bought? Okay, so let us now first of all try to see what we are given in this example. So the customer has bought 12 pieces of fruit, each of which is either an apple or an orange, and the total cost is $1.32, or in other words 132 cents. Now what additional are we given? An apple costs 3 cents more than an orange, and also more apples than oranges were bought. Then how many apples and how many oranges were bought? Note that we have to find two things: the number of oranges purchased and the number of apples purchased. But something else also is there that we don't know, namely how much an apple costs, or for that matter how much an orange costs. That also we don't know. So I am writing it as a solution, not formally, but we are just going to see the equations. So let me just at least write, let x apples and y oranges were bought. Okay, so these are two variables. Also, because we don't know the cost of each apple or each orange, also let each orange cost z cents or z cents. Then how can we translate this into an equation? We now actually have not only one equation, but in fact two equations and one inequality. You see, y oranges were bought, and according to us each orange costs z cents. So the total cost of the oranges is y times z, and the total cost of the apples is how much? X times z plus 3. Because each apple costs 3 cents more than an orange, and because everything is in cents, so the total cost is 132 cents. So this is one equation. The other equation that we have, and which in fact comes even before this, is that a dozen pieces of fruit they have been purchased or bought. So that means the total number of apples and oranges should be equal to 12. This is the other equation, but there is an inequality also. More apples were bought than oranges. Okay, so we can in fact see that although here we have two variables, but here we have three variables. Using these two equations, we can in fact eliminate one of the variables, which the author has done. He has eliminated y. So that means he has used this substitution, y equal to 12 minus x here. And if one does that, one ultimately ends up with this equation involving x and z, this particular equation. I am showing things extremely informally, just showing the necessary part. And the equation that one ultimately gets is this. Where is it? Oh, I have actually gone through the calculation here. Anyway, so this is the one that one gets. Now this is the Diophantine equation where we need to find x and z. Now one particular solution is this, x naught equal to minus 132, and we do not have y here, but you understand that this is just a second variable. The actual variable name does not matter. And this is, I think it is 44 only. Yes. But then the general solution would look like this, x equal to x naught, that means minus 132 plus bt, that is 4t, this is b, and z equal to z naught plus 80. No, sorry, minus 80, because this one is plus, the other has to be minus 80, a is 1, so this is t. Okay, so this is the general solution to this equation. Now from this we need to actually find our solution which we want, where these are not just arbitrary integers but they represent something. This represents the cost of an orange, and this represents the number of apples purchased. So for that, then what the author does is that the author considers this inequality. But where is this thing coming from? The first inequality we understand. It comes from here, since x and y, none of them can be a negative integer because they are, after all, the numbers of some objects. So x cannot possibly be greater than 12 because then y has to be negative, which does not make sense. So the first inequality we understand, it makes sense. However, what about the second one? Immediately we cannot see y, but let's see what happens if this is considered to be false. That means if x is less than or equal to 6, what problem do we then encounter? You see, say to make matters even simpler, you consider x to be equal to 6. Okay. Now if x is 6, then what is your y from here? Y also has to be equal to 6, but then this inequality is violated. So this is where this inequality is used. So x cannot be equal to 6. In a similar manner, x cannot be less than 6 also, because if x is less than 6, then y has to be greater than 6. But then clearly this inequality again is violated. So that is why this cannot be the case. So x has to be greater than 6. Then what we do, we use this expression for x in these inequalities. That means we write this plus 4t greater than 6, and they lead to again two inequalities that t has to satisfy. The first, ultimately we get this 36 greater than or equal to t, and t should be greater than 34.5. Keeping in mind that t after all is an integer, this gives us exactly two values of t, 35 and 36, and corresponding to them we get two sets of values for x, y and z. When t is 35, x, I think it becomes 8. You can just simply put the values and calculate. Then x becomes 8. So y becomes 4 because their sum has to be 12, and z becomes 9. How do we express this solution? That means if this is the case, then 8 apples were bought for 12 cents each, and 4 oranges were bought for 9 cents each. Because this is the cost of one orange, this is the price for one orange. Similarly, when our t is 36, when t is 36, then x becomes 12. So then y has to be equal to 0, and this, in this case, z or c becomes 8. So that means no oranges were bought. That is also one possible solution. "12 apples were bought for 8 plus 3, because we cannot take just simply z, but z plus 3, 11 cents each." And you can in fact see that 12 times 11 is 132 cents. So that is the total cost. So this way the problem is solved, and it has two possible solutions. After this, in fact, towards the end of this section, after this, a little history about this type of problems is given by the author, and he says linear indeterminate problems like these have a long history, occurring as early as the 1st century in the Chinese mathematical literature. Owing to a lack of algebraic symbolism, they often appeared in the guise of rhetorical puzzles or riddles, much like this one. And the contents of the mathematical classic of Chang Chiu Chien, I am not sure whether I am pronouncing it correctly. If I have butchered the name, I apologize. Okay. In the 6th century, this mathematician wrote something, a classic book which had this kind of problems, and one of the most famous, in fact the most famous according to Burton, of these problems in indeterminate equations is the problem of 100 funnels. And the statement of the problem is this: if a cock is worth 5 coins, a hen 3 coins, and 3 chicks together 1 coin. How many cocks, hens and chicks totaling 100 can be bought for 100 coins? I think I need more ink. Okay, so in this problem, a cock is worth 5 coins, a hen 3 coins, and 3 chicks together they cost 1 coin. So how many cocks, hens and chicks totaling 100? That means their total number should be 100, can be bought for 100 coins. So the total number of objects or rather the total number of these parts should also be 100, and the total cost should also be 100 coins. That is the question. And in the solution you can in fact you will have to introduce these variables. So let x cocks, y hens and z chicks were bought. Then we are going to get 3 equations. One of them is just simply x plus y plus z equal to 100. This is the total number of items purchased, and the other one is about costs in coins. So 1 cock is worth 5 coins, so that means 5x plus 3y plus, is it 3? Yes. And 1 chick is worth 1/3 of a coin. This is also equal to 100. And here also one of the variables can be eliminated, and the author has eliminated this one by using this substitution, 100 minus x minus y. Now when one does that and substitute this expression here, we get an equation. and the equation that we get is ultimately, I mean, after simplifying everything and doing everything that needs to be done, ultimately we get 7x plus 4y equal to 100. And as a particular solution to this Diophantine equation, the author has used this x naught equal to 0 and y naught equal to 25, which is just very easy. 7 creates problem, so eliminate 7 altogether by choosing x equal to 0. And because we have this option, if we take y equal to 25, then we are already getting 100. So all the solutions are of course x equal to, we won't have any x naught here, plus b. Oh, by the way, in this case also you can see that 7 and 4 are relatively prime, so that means our d is 1, the GCD is 1. 4t, just simply 4t, and y is equal to y naught minus 7t. And if we use these values, then we get an expression for z also, and that expression is in terms of t. That expression becomes 75 plus 3t. Now the author Chang himself gave 3 answers which look like this: x equal to 4, y equal to 18, and z equal to 78. This is, they constitute one solution. Then x equal to 8, y equal to 11, and z equal to 81. X equal to 12 cocks, 4 hens, and 84 chicks can be bought, or 8 cocks, 11 hens, and 81 chicks, or 4 cocks, 18 hens, and 78 chicks can be bought. Now if one wants to find these values, say from this general solution, one can, of course, in this case we do not need any clever trick like what we needed to do in the previous example, namely 12 greater than or equal to x greater than 6. In this case, just one considers the condition that all these things have to be positive. One considers these conditions, and after solving these inequalities for t, one gets these exactly 3 values for t that are permissible if these inequalities are to be satisfied, and these 3 values correspond precisely to these 3 values. So these are the only solutions to Chang's problem, and this is where this section ends, and this chapter also ends. So in the next number theory video, we are going to solve the exercises that come after this, and then we will start, we will go to the next chapter which treats primes. So now only things are going to get more interesting. So that will be all. I wrap things up here itself, and tomorrow we are going to again solve Gallian problems from group theory. So that's just it. So see you tomorrow with Gallian. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.